Good morning, gang. All right, we're pretty much ready to go here. I just need to swap out a couple of papers and we'll be ready to get started. Today, we're going to talk a little bit more about volumes. I want to approach the disk washer thing from a slightly different perspective. And if there's time, I'll introduce the cylindrical shells method also. Okay. Let's make sure this dot camera, it's all closed. Okay. Turn this on, and we're ready to go. This is now the 2nd of September. Just a quick word of warning. We don't have class next Monday. Let me make sure actually that I accounted for that. I'm not sure that I did. Reset. Okay. So because we don't have class next Monday, I am going to go in here to WebAssign. I'll show you. There's no reason you can't see that. And change those due dates a little bit. I don't like the idea of having something be due on a day you and I don't meet. So I'm going to push these second homework sets to Wednesday. Or I could have them be due earlier. Nah, Wednesday's better. Wednesday's better. Let's do that. So we'll reschedule to week. No, we can stay within the week. It's just gotta go. So the stuff you're working on right now, homework 2, normally it would be due next Monday, but I was just reminded because I wanted to remind you that next Monday is Labor Day. So we will not be meeting. The college is closed, which means even these hybrid or online classes have to be inactive on those days. Labor Day was a holiday that was fought and won for by labor unions, so it's worth taking the time to remember, just like we do for Veterans Day and everything else, to remind ourselves why the holiday is a holiday. And I don't want you stressing about this stuff instead of doing that. So these will be due on the 9th instead. Okay, so with that said, all the problems we looked at on Monday for this volume stuff, at least, all the volume problems we looked at on Monday, the integrals ended up being dx integrals. But just like with the area problems we saw, sometimes it's more natural to set things up as a dy integral. So remember, in the slicing method, you get to pick the name of the axis you run through the things. So there's no reason to ever have any confusion about what your integral is being done with respect to. But with the disk washer method, so we're still in section 6.2. How do we know whether we're going to be doing a dx integral or a dy integral? And the answer here is, remember the strip. We draw is always, and I hope you'll forgive me for this, I'm tired of writing out the word perpendicular. There's a symbol that mathematicians use for the word perpendicular. This, it's read perp. To the axis of rotation. So really, it's the axis of rotation that determines whether you'll be doing a dx integral or a dy integral. If the axis of rotation is a horizontal line, then you'll be drawing your strip oriented up and down, which means that thickness, the little differential thickness, is a dx thickness. And that's what we've seen every time we've done one of these problems so far, because we've been rotating about the x-axis, or about the line y equals 1. But sometimes we'll rotate about the y-axis, or even stuff like the line x equals 1. And in those cases, the strip will be drawn in horizontally, so perpendicular to the axis of rotation, which means its thickness will be a little up and down thickness, will be a little dy thickness. And that means that our integral will have to be done dy, and that means we'll have to characterize all of the distances we need in terms of the variable y. So I want to start with a kind of gentle example like that. I'm pretty sure, yeah, we've got one here. So y equals x cubed, y equals 8, x equals 0 about the y-axis. By rotating the region bounded by y equals x cubed. What were the other ones? Y equals 8 equals 0. About the y-axis. Okay, so first I'm going to draw this region. Y equals x cubed, like this. Y equals 8, it's a horizontal line. So I can say that's right here. Y equals x cubed is right here. And the line x equals 0, that is the y-axis. So this is our region. And we want to spin it around this guy. So this is the y-axis, this is the x-axis. If I draw in my strip perpendicular to this axis of rotation, my little differential thickness strip, that'll look like this. And if I were to rotate just that strip, if you imagine this guy spinning around, that would give me a disk. So this is definitely a disk problem. There's no gap between the end of the strip and the axis of rotation. So it's not a washer, or you could say that the little r inside is 0. So here's my dy thickness. And I'm trying to draw this so you can kind of see it as coming from rotating that. So I'm drawing the axis of rotation is going through there. And of course, the radius of this apparatus is big R. And this solid here, this is my dv solid. Right, so the little volume I get just from rotating the strip looks like this, and I call that little volume dV. As always with the disk washer method, it's pi times big R squared minus little r squared, and in this case, dy. That's why when I gave you those formulas, I wrote dt here instead of dx, because sometimes it's a y, sometimes it's an x. So it's easier to just give you the formulas in terms of another parameter, t, and then leave it to you to determine whether to use x or y on a given problem. We've already observed that little r is equal to 0. And then to figure out big R, I'd like to come back here and label it. Remember, big R is always the distance from the further end of the strip. Look at those formulas I gave you at the end of class on Monday. Distance from the further end of the strip to the axis of rotation. So here the y-axis is the axis of rotation. So here's big R. And little r would be the distance from the near end of the strip to the axis of rotation. But that's clearly 0 because the strip extends all the way to the axis of rotation. There is no gap between the near end of the strip and the axis of rotation. The catch here, this point, which I would normally think of as x comma x cubed, because it's along the curve y equals x cubed, I now need to characterize in terms of y. For what reason? Well, because I can't say r equals x, because I can't integrate x squared dy. That doesn't make sense. So how can I recharacterize this point in terms of the variable y? That becomes the question. Can anybody help me with that? Snapshot. Yeah, Margaret got it exactly. We should take this equation, the relationship between x and y along that curve, and solve it for x. So y equals x cubed, that's the same as saying the cubed root of y equals x. Which means that this point is the same as the cube root of y, comma, then what would go in the y coordinate? So x is the cube root of y, so that's what goes in the x coordinate. What goes here? Yeah, just y, because now I'm thinking of y as being my independent variable. Good, okay. So this is what I mean by recharacterizing that point in terms of y. Here I have a point on the curve, y equals x cubed, characterized as a function of x. Here I have a point on the curve, y equals x cubed, characterized in terms of the variable y. And now when I have this guy, I can take the same distance and rewrite it instead of as x, because this distance would be x normally. So that's the horizontal displacement of that point. I can write that distance as the cube root of y, because the cube root of y is x. So here your first thing might be to write r equals x, because that's what it looks like. But then you realize, oh shit, I need everything in terms of y. So then you go, oh wait, that's the same as this. And now you can finish writing down dv. So dv has to be pi times the cube root of y squared minus 0 squared dy. And so this is the thing that I'll have to integrate in order to recover my volume. That's the volume of the little solid that I get just from the strip. And now I have to imagine all the little solids I would get as this strip moves from all the way down here to all the way up here. And when you stack all of those infinitely thin solids, you'll get the overall solid whose volume I'm trying to find. So what is V? Well, v is the integral of dv. And like we said, we have to imagine the strip is moving from down here, where y is equal to 0, all the way to up here, where y is equal to 8. So I have to imagine the strip as moving through this region. So I'll be integrating from 0 to 8. And what is dv? So that's the integral from 0 to 8 of pi times. This is y to the 2/3. Maybe I'll write it one more time. It's just the cube root of y squared. The minus 0 is 0, so I'm not going to do anything with that, times dy. And then we'll just use some algebra to write that. Yes, Griffin, yes. Little r is 0, because little r, remember, is the distance from the near end of the strip to the axis of rotation. And it's that gap that creates the gap in the washer. But since there is no gap between the near end of the strip and the axis of rotation, little r is 0. So I'll come back here, I'll pop out the pi. I have the integral from 0 to 8. The cube root of y squared is y to the 2/3 power, and I'm integrating dy. From here, things are easy. It's a power rule integral. So this is pi times, I have to increase this power by 1. 1 I can think of as 3/3, so that would be 5/3. And I have to divide by that new power. That's the same as multiplying by 3/5. And then I have to evaluate between 0 and 8. Now down here at 0, this whole thing will be 0. That's not too exciting. So all the fun comes from plugging in 8. This will be pi times 3/5 times 8 raised to the 5/3. And believe it or not, this number is actually not too bad. Usually when we see weird roots like that, we expect irrational numbers. Okay. So the limits of integration, the bounds, I have to imagine this strip as moving from the very bottom of this region to the very top of this region, right? Because I'm thinking of my solid as being infinitely many of these little guys stacked on top of each other. I think of each of them as being infinitely thin, and then when you stack infinitely many of those infinitely thin little volumes together, you get the whole volume. Think of this picture, right? So I've got all these little disks, and the way I add up the infinitely many, infinitely thin disks is by thinking of this strip as moving from down here, where y is equal to 0, to up here, where y is equal to 8. The 8 comes from this boundary curve. They told me that the upper bound on this region is the horizontal line y equals 8. So for that strip to move through this whole region, it has to go from y equals 0 all the way up to y equals 8. Okay, sorry, responding to a question in chat there. What was I saying? Yeah, this number is not too unreasonable. It might look like it would be weird because of the weird power, but 8 is actually a perfect cube. So remember, 8 is 2 cubed, so this is 3 pi over 5 times 2 cubed raised to the 5/3 power. And then the cube and the 5/3, they interact. So I'll have 3 pi over 5 out front. That's the same as 2, come on, 10, to the 3 times 5/3, and these cancel. So the 3's cancel. I get 2 to the 5, which is 32. So this is 3 pi over 5 times 32, because 2 to the 5 is 32. 32 is not divisible by 5, so there's nothing nice that's going to happen there. You could multiply these, I guess, and you get, what, 96? Pi over 5. I would be perfectly happy with you stopping here. I would like to see you recognize that this simplifies, right? You could stop here. It wouldn't be incorrect, but I would like to see that you guys recognize that this cleans up. Because it does. It cleans up not just to a nice number, but to an integer, which is like an exceptionally nice number. Okay. So questions on the setup. Are we all comfy with how we knew to draw the strip like this? That tends to be the first and biggest hurdle. Once you've got your region sketched and your strip drawn in appropriately, everything else you can kind of follow your nose. Do we all understand why we draw the strip? All of the distances in our formula, the r's, even the dy, all of those things come from analyzing the picture with the strip drawn in. The 3/5 is the reciprocal of 5/3. So at the integration step here, where I added 1 to the power and divided by the new power, adding 1 to 2/3 gives me 5/3, because 1 is 3/3. So 2/3 plus 3/3 is 5/3. And then instead of writing this as y to the 5/3 divided by 5/3, I decided to go ahead and do the divide by 5/3 as multiply by 3/5. So I'm kind of just saving a step. If you wanted to, you could sneak the extra step in here. This is pi times y to the 5/3 divided by 5/3 from 0 to 8, like that. But then dividing by 5/3 is the same as multiplying by 3/5. So I'm thinking that we've done enough of these power rule integrals now where we should be getting comfortable with that particular arithmetic step. But there's nothing wrong with writing this. So the 3/5 is the reciprocal of this guy. It's good. I'm glad you guys are asking questions. I'd love to know whatever else you're thinking, whatever else you're wondering. I know it's early. Try to play along. Anything else on this? No, that's okay. Yeah. Maggie, please. What's up? Yeah, that's interesting, right? So if this was a dx problem, if the strip had been oriented vertically, then the way I would choose my bounds is by imagining that strip sliding left to right through my region. So my lower bound would be whatever the smallest x value in that region was, and my upper bound would be whatever the largest x value in that region was. But here, because my strip is horizontal, I'm imagining it moving down to up. So my bounds come from whatever the smallest y value in my region is to whatever my largest y value in my region is. This is why in those area problems, we had you guys drawing that strip in on the last few problems. So you could kind of picture the area as having been swept out as the strip moves either from bottom to top or from left to right. Same sort of thing is going on here. So your bounds in a dx volume problem will come from the smallest x value in the region to the largest x value in the region. And the bounds on a dy problem will come from the smallest y value in your region to the largest y value in your region. Sometimes I find it helpful at this step to write in the variable that's giving me the bounds to help remind me. So rather than just writing 0 to 8, write y equals 0 to y equals 8. And on the x dx problems, you can write x equals whatever to x equals whatever, if that helps you keep straight in your head. Okay. Okay, cool. Yeah, I'm glad you like that. So I'd like to take a look at one more problem like this, a disk washer problem that's oriented with a dy integral. And then I'm going to introduce to you the next method, which is the method of cylindrical shells. But before then, one more. Let's find the volume of the solid obtained by rotating. And again, I'm not going to write the words the region bounded by the curves. I'll just say by rotating this is one of my favorite little volume problems because it requires that you kind of understand everything. This particular problem, or some little variation of this problem, often shows up on my first test. I know it's early, so I'll say that again. This particular problem I like a lot, and some variation of it often shows up on my first test. So let's take a look. I'm going to graph these curves. One reason I like it is because folks have a tendency to forget some of these less common graphs, like the ln. So you got to know what y equals ln x looks like to even get started here. So I'll remind you. Ln x has a vertical asymptote as you approach 0 from the right. He pokes through at 1, 0, and then he grows like this, very, very slowly, like that. Okay. So this is what the natural log looks like. This number here is 1, this number here is e, and the point up here at x equals e is e comma 1, because the natural log of e is 1. So the region I'm playing with is this region. And then I want to rotate this about the line x equals -1, which is over here. So my axis of rotation is not one of the coordinate axes. There's a few problems like this in your homework, where the thing that you're rotating about is neither the y-axis nor the x-axis. It's some other line. My axis of rotation here is still a vertical line. So I'm going to kind of set things up the same way I would if I was rotating about the y-axis, meaning since I'm using the disk washer method, I need to draw my strip in perpendicular to the axis of rotation. So my strip will be drawn in like this, oriented horizontally. Let's go ahead and do that. Okay, so here is my little differential thickness strip. Its thickness is a dy thickness. And then I need to identify r and little r, because we know dv, I don't quite have room here to sketch the solid quite to size, but I'll do my best. So there's my inner. There's my outer. So here we do have a gap between the nearer end of the strip and the axis of rotation, which means we will have a washer shape here rather than just a disk. My 3D skills are definitely limited, but that's about as good as I can do for that. I know that this thickness here, again, is a dy, but now I have two radii to go after. I have to find this little r, and I have to find this big R. So having drawn this, thinking about just this strip rotating about this axis of rotation, I need to come back to this picture here and label little r and big R. So somebody help me out. What is little r? You don't need to tell me the exact expression, but maybe it's not 1. No, I mean, the algebraic expression for little r, you're actually going to discover is somewhat complicated. But in terms of distances, Maggie's got it. All right, yeah. So this, look at what Maggie typed at 8:34 in the chat. I keep saying this, and there's a reason for it, because that is the only safe way to define what little r is. And similarly, the definition of big R, the only safe way. That's okay, I didn't even see it. So little r is this distance. Always the distance from the nearer end of the strip to the axis of rotation. So here is little r. And big R is always the distance from the further end of the strip to the axis of rotation. One of these is constant, but it's not little r, it's big R that's constant. The far end of the strip is always touching this boundary, and the axis of rotation is always right here. So as this strip moves up and down through this region, you know, you can imagine that the strip was down here. Big R would still be from here to here. It would still be the same. So let's take care of big R first. What is big R? It's the distance from here to here. What is that distance? And it's worthwhile though. This is, like I said, this is why this is a problem that I like, because it's full of little places you can get tripped up unless you remember the definitions exactly. Yeah, Griffin's got it, and Juan, and Emily. 1 plus E, right? Because this distance from here to here, that's E. This distance is 1. So overall, this is 1 plus E. Or you can think of it as E minus negative 1. Comes out to 1 plus E, or E plus 1. What about little r? Little r is a bit tougher because I need to know the x coordinate right here. Right? It'll be whatever the x value is right here minus whatever the x value is right here. It'll be this distance, yeah? So that's a horizontal distance, so it'll be a difference of x values. And remember, I'm along the curve, y equals the natural log of x. So normally I would think of this point as being x comma ln x. Well, remember here, everything has to be given in terms of y. So let me first write it like this. I don't have a whole lot of space in here. So that's x comma ln x that I've written in here. I would be tempted to say, yeah, Nick's got it. Maggie and Nick both have it. I would be tempted to say that little r here is x plus 1. But if y is equal to the natural log of x, then e to the y is equal to x. So x plus 1 is e to the y plus 1. And take a second and make sure you're really comfortable with this. The picture is quite busy. There's a lot going on here. So y equals ln x, if you solve this for x by exponentiating both sides base e, you get e to the y equals x. So the x coordinate right here, normally we would just call that x. But we could instead think of this point as being e to the y comma y. That's the same thing. So this distance, little r, is the horizontal distance from this point to this line, which is either x plus 1 or e to the y plus 1, depending on how you would choose to think about it. Since my thickness is a dy thickness, I need little r to be a function of y, so I can do the integral, which means instead of writing it as x plus 1, I should write it as e to the y plus 1, because x is e to the y. Okay, now we're ready. So now dv, that's pi times cap r squared minus little r squared dy, which is pi times cap r is e plus 1, and little r is e to the y plus 1. So that's how this setup would look. So I think this is a good place to pause and take a second. We've gotten a lot of good feedback from you guys, but I'm sure there's also a lot of questions. So what feels weird? What's hard to see? What are we thinking? So the little r distance, let me, okay, sure. Let's see, I don't want to cover that because I'm sure folks are still thinking a little bit. I don't know, it's nothing here that's not worth asking. So, so the graph y equals ln x is made up of all the points of the form x comma ln of x. If you solve this for y, or sorry, solve for x, then you exponentiate both sides. Remember, that's how you get a variable out from inside of a natural log. You have to exponentiate. meaning to put in the exponent of, or I've heard calculus students call this e-ing both sides. That's fine. E to the y is just e to the y, but e to the natural log of x, those cancel and just give you x. So this is how we solved for x. And that means that you could also think of this graph as being made up of the points e to the y, comma y. And then the distance here, I take the larger x value and I subtract the smaller x value. So little r, you could think of it as x minus -1, which is x plus 1. Or you could think of little r as e to the y minus -1, which is e to the y plus 1. Because the x value here is -1, right? This point I could call -1 comma y. So I'm putting it at the same height. I'm trying to put it at the same height as that point. So you take this x value and then you subtract this x value. So you could do x minus -1, which is x plus 1, or equivalently e to the y minus -1, which is e to the y plus 1. Cool? Okay. So then let's go ahead and see if we can do this integral. In a moment, I'm going to set the same problem up for you another way, and that'll lead us to a neat challenge. I'm going to copy my dv down here. So dv was pi times e plus 1 squared minus e to the y plus 1 squared dy. I'm going to need to pick some bounds here also, right? So let's think about that. It's a dy integral. So I need to ask what's the smallest y value in my region and what's the largest y value in my region. Good, 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 good. Yeah, so v will be the integral from y equals 0 to y equals 1. So the largest y value in the region up here is 1, and the smallest y value in the region down here is 0 of dv. So that's the integral from 0 to 1 of e plus 1 squared minus e to the y plus 1 squared dy. Now this integral isn't too bad. You could do this integral minus this integral. That's not a bad way to do it. Or you could multiply everything out. I'm tempted to do it the first way because this is a constant. But I think the thing that most people want to do when they see this is to FOIL everything. So let's do that, even though that's a constant. That'll be e squared plus 2e plus 1 minus e to the 2y plus 2e to the y plus 1 dy. And most of these terms are constant. All three of these are constant. This is constant. We can put the ones together, they'll cancel. The only things that are going to require any careful work are these. So I'll have integral 0 to 1 e squared plus 2e, and then this plus 1 and this minus 1 cancel. We distribute the minus, right? And minus e to the 2y minus 2e to the y dy like that. Oh, thank you. Yeah, where did my pi go? It's here. You saw nothing. I'll bring it back out front in the next line. Sorry, good catch. Yes, thank you. All right. And then, let's see, I don't think there's any other simplification we can do. So I'll bring my wandering pi back out front. And now we'll find our antiderivatives. This is constant, so that'll be e squared y plus 2e y. When you integrate a constant dy, you just slap on a y. The e to the 2y integral is going to require a little bit of love. So we might come off to the side and ask ourselves, how do we do the e to the 2y integral? We haven't done a whole lot of those. Let's see, where can I come off to the side to do that without cluttering things? We'll do it here. How do I integrate e to the 2y? Yeah, Maggie's got it. This is like a little micro u sub. I could let z be 2y. dz is then 2dy. I'm going to do this as an indefinite integral because these little micro u subs we want to get really quick at. So this would be 1/2 dz is dy. So I'll have 1/2 integral e to the z dz, which is 1/2 e to the 2y. So the e to the 2y piece is going to give me a 1/2 e to the 2y. So I'll have minus 1/2 e to the 2y. And then the 2e to the y is just going to stay 2e to the y. And this is all evaluated from 0 to 1. So these little substitutions where your new variable is a constant multiple of your old variable, I have a name for these. I call these micro u subs or micro substitutions. They change so little, right? It's something you want to get to a place where you can do these kind of in your head, I guess is what I'm saying. You want to get to a place where instead of going off to the side and doing this calculation, you can say, oh, well, if this was just e to the y, then the integral would just be e to the y. E to the 2y, well, I would want to substitute u or z equals 2y, so I'll just get a 1/2. Another way to think of it is if you differentiate e to the 2y, you get 2e to the 2y. So the integral of e to the 2y should be 1/2 e to the 2y. If you prefer to split this integral up and do the substitution properly on this piece, I totally understand, especially at this point, because this is still relatively new for some of us, depending on how well your last class treated u sub. In any case, we get here. So each of these just get y's slapped on because they're constants. This guy is easy. Integrating e to the y always just gives you e to the y. This guy involves a little micro substitution that gives me a 1/2 out front. But otherwise, e to the 2y integrates to e to the 2y. And from here, all that's left to do is evaluate. If I plug in 1, I'll get these two constants, e squared plus 2e. Plugging 1 into these, I'll get minus 1/2 e squared and minus 2e. And then I'll subtract what I get when I plug in 0. These will both be 0. This will be minus 1/2 times e to the 0. That's just minus 1/2. And this will be minus 2 times e to the 0. That's just minus 2. So I can combine some like terms. This e squared and this minus 1/2 e squared. That will give me a positive 1/2 e squared plus 2e minus 2e. Those go away altogether. And then here I'll distribute this minus, or I can combine these guys over here. So negative 1/2 minus 2. 2 is 4/2, so that's minus 5/2, and then the minus here makes plus. Like this. So another way to think about that e to the 2y integral step is to just remember that the integral of e to the ax is 1 over a e to the ax plus c. Similar to how e to the ax primed is a e to the ax. Focus, God damn it. I feel like this is so washed out. There we go, that's a little better, right? So this rule is useful. We'll use it a lot, and we'll use a lot of similar things like that. So these little, I call these micro substitutions. They're good to get to a place where you can do them in your head. They're like these really simple chain rule problems. Questions on this? Okay, I'll give just a minute or two for people who are writing or making little notes for themselves. But then I'm going to introduce this new method. So we're going to start talking about section 6.3 next. What am I doing for time? Yeah, perfect. The minus sign here got distributed over these. So this became minus e to the 2y and minus 2e to the y and minus 1. And then the minus 1 that I got after distributing this negative here canceled with the plus 1 here. Is that the minus sign you're asking about, Zach, or is it a different minus sign? Right? Sure? So I distributed this minus, and then here I combined these and then distributed this minus to get the plus 5/2. The minus here went away because I combined it with this positive one. So 1 times e squared minus 1/2 times e squared gives me positive 1/2 e squared. And these two ate each other up perfectly. Okay. Okay, so I am going to move on now. I'll come down here. There are some problems that are not suited to the disk washer method. So you'll see in a minute, there are some problems that can be worked either way, but there are some problems where you just cannot attack using the disk washer method. And the textbook does this well, and unfortunately it doesn't come over into the WebAssign stuff very nicely. So I've included an example. This one. I don't think this was the one I had in mind, but that would work also. The one I usually like to think about here is, no, we're getting too far ahead of ourselves, God damn it. There we go, this one, sine of x squared. So, let me copy that down. So this is section 6.3, volumes by cylindrical shells. Imagine we want following volume. So this curve is y equals the sine of x squared, which means that this guy right here is the square root of pi, and I want to revolve around the y-axis. If I wanted to set this up using the disk washer method, I would have to draw my strips in like this. And so little r would be this, big R would be this. So I would need to characterize these distances as functions of y, which would mean I would need to solve this for x. Right? This point right here, I can think of this as x comma sine of x squared. But this point over here, I would have to think of it the same way. This is also like x comma sine of x squared. But of course, these are different x's, because this one is like right here, and this one is like right here. So the question of how the hell do I describe little r and big R as functions of y becomes an issue. There's no nice way to solve this for x. We can use sine inverse. I could say, okay, well, sine inverse of y must be equal to x squared. So I take the inverse sine of both sides, and then I say plus and minus the square root of sine inverse y equals x. But the terrible sad truth is that would only work up to this point. That would not work to the right of here. Because remember the way the sine inverse function is defined, you have some domain restrictions. Sine inverse only plays nice out to pi over 2. Beyond that, he hates us. Not that he hates us, he just doesn't exist, right? You can only invert the sine function from negative pi over 2 to positive pi over 2 because it's not 1-to-1. And that's the real issue. Because the curve y equals sine of x squared is not 1-to-1, I can't recharacterize the points x comma sine x squared in terms of y as required to set up the volume integral. Here. So I mean, I can draw the picture, but I have no way to write r as a function of y. I have no way to write little r as a function of y. So I'm kind of stuck at this point. I'm stuck because algebra, because I can't nicely solve this. This might look like I've done an okay job of solving for x, but the truth is this only works if y runs from 0 to 1. This only works as x runs from 0 to pi over 2. Really the square root of pi over 2. Yeah, 0 to the square root of pi over 2, which would be right here. So this wouldn't work to help me find big R. I could use this to find little r, but then what do I do over here? There's no way for me to describe that because I'm outside the domain restriction associated with the inverse sine function. You might ask, are there not incredibly clever ways to get around this? Yes, there are. But they're incredibly clever ways to get around this. It's not at all straightforward, and it's not something that you'll be able to write down nicely in terms of algebra, which means it's not something that is even approachable for us. So what we need for this problem and other problems like this is a new method, a method that doesn't care about the fact that this function isn't one-to-one, a method that doesn't care about finding this distance separate from this distance. And that's the cylindrical shells method. So this is an example of a problem that even though you can draw the picture and you can kind of start writing things down, the disk washer method falls apart. And this is why we have the new method. It's called cylindrical shells. So let me introduce this new method. I'll stay here for just a second longer in case anybody's writing anything down. I would like you to reflect on this. There is one problem in your homework that will ask you to reflect on this a little bit. So it is worthwhile to think about what's going on here. It's really just because this function is not one-to-one. That's the main issue. If we chopped right here, and I was only looking at like this piece here, then I could do that using disk washer. That would be okay. There I could use this. It would be ugly as hell and you'd never get the integral done. Can you imagine trying to integrate this son of a bitch? Hell no, hell no, hell no. So that even if you did that, even if you didn't look at the full problem, you just looked at this part of the problem, the integral would be unmanageable. And you can't do the full problem. So how do we attack this? Well, it turns out there's another way to think of these volumes. Rather than being stacks of disks, I can think of them as being concentric. Yeah, that's okay. We'll be done in about 10 minutes. I can think of them as being concentric shells. So instead, same curve. Same axis of rotation, same region. Instead of drawing my strips perpendicular to the axis of rotation, if I draw my strips parallel to the axis of rotation, I'll get a new differential solid, dV. If I spin just this strip around this axis of rotation, the thing I get doesn't look like a disk. It's not very, very thin at all. It's quite tall. It would look like this. It'll be like a soup can with the top and bottom cut off. It has a very thin wall. The wall thickness is dx, right? So if this thickness here is dx, then this thickness here is dx. And I'll have a meaningful amount of height. This height will be this height. And so you can see it looks like a cylinder, but it's really not the whole cylinder. It's just this little shell. So we call this method the method of cylindrical shells. All right, think soup can. With the top and bottom cut off. Like this. So this is your dV. And in order to get a nice formula for the volume of this cylindrical shell, what I do is I imagine I can take some very sharp scissors and cut and then unroll. And when you cut that and unroll it, you will get a little rectangular prism. So this wall thickness, that's still dx. Here, if I call this h, this is h. This guy, the kind of length of this thing. So I've taken my very sharp scissors and I made a cut here, and then I unrolled it. And that gave me something like this. This height is still this height. This length here corresponds to what dimensions of the cylinder? Yeah, good, it's the circumference. So if this thing had radius r, then the circumference here is 2 pi r. So your differential volume, dV, the volume of this cylindrical shell, is 2 pi r h dx. And then we come back to this guy, and we try to say, okay, well, what corresponds to the height? What corresponds to r? I think it should be fairly clear that this is the height, and that this is r, right? The distance from the axis of rotation to the strip, that's your radius, sorry, the distance here, horizontal distance from the axis of rotation to the strip, like that. And then the height of the strip is the height of the cylinder. This point, remember, is x, comma, sine x squared. So r is just the horizontal distance from here to here, that's x. And h is the vertical distance from here to here, that's the sine of x squared. There's no bizarre algebra. So for this particular problem, dV is 2 pi times x times the sine of x squared dx. And that is something, not only can I write it down easily, I can integrate it. So here r was equal to x, and h was the sine of x squared. Okay. So we've got just a few seconds left. My integral is a dx integral because my strip is oriented up and down. Its thickness is a dx thickness, which means my bounds need to be x bounds. The smallest x value in my region over here is 0. The largest x value in my region is the square root of pi. So as always, v is the integral of dv. And here it's going from x equals 0 to x equals root pi, one of my favorite numbers. And the thing we're integrating is 2 pi x sine of x squared dx. And that integral at a glance might look a little bit frightening, but it's really not bad at all. You can pop out the 2 pi. Integral 0 to root pi x sine of x squared dx. This was an integral that we did in our first homework. I think we did it as an indefinite integral without bounds. We need to substitute for x squared. So I'll let z be x squared. dz is then 2x dx. When x is equal to 0, z is equal to 0. And when x is equal to the square root of pi, z is equal to pi. My x dx is right here. That is not exactly dz, it's 1/2 of dz. So I'll get 2 pi times the integral from 0 to pi. Sine of x squared is the sine of z, and then x dx is 1/2 dz. The 2's and the 1/2's will come together. And I'll get pi times the integral from 0 to pi of the sine of z dz. Now, who has sine z as a derivative that's not cos z, but negative cos z? So this is pi times negative cos z evaluated from 0 to pi. So that will be pi. I'll give myself a little more space here. Pi times the negative of cos pi minus the negative of cos 0. The cosine of pi is -1. Negative cos pi is +1. Minus negative cos 0. Well, cos 0 is 1. Negative cos 0 is -1. Minus -1 is the same as +1. So this is 2 pi. So the volume here is not some crazy weird number. And it's not crazy hard to figure out as long as you use the right method. So this method, where you draw your strip in parallel to the axis of rotation, leads to a differential solid that looks like a tiny cylindrical shell, or a cylindrical shell with very, very thin walls. The formula for dv here is 2 pi rh and then dx or dt. I would write this as dt if I was giving you the formula in general, because sometimes it'll be dx, sometimes it'll be dy, depends on the problem. Any given volume problem, you can attempt to attack either way, using the shells method or the disk washer method. What you'll see is that sometimes the integral is easier one way or the other. Sometimes you need the disk washer method, sometimes you need the cylindrical shells method because of the algebra. So there are some problems in your homework this week. If they say that they're from section 6.3, you can assume that they're meant to be attacked using the cylindrical shells method. And if they say they're from 6.2, you can assume they're meant to be attacked using the disk washer method. I think there's one problem in there that requires the slicing method. But you guys are now equipped to handle all of the homework problems for this week. And then on Friday, we're going to get more practice with the shells method. I'll come back to that lnx problem we did earlier, and I'll show you how to attack that with the shells method. We'll see that that leads to an integral we're not quite yet ready for, but it's still a nice setup. Yeah, it's good stuff. So real quick, before you guys leave, and I know everybody's anxious to get out of here, there are some animated GIFs for volumes, cylindrical shells, and I've seen that are very nice. I think this is the one I'm thinking of. This is the very first one. What page is this coming from? Here. No. This looks right. Where's the display? Show region. Is it? No! That's where. Ah, shit. All right. These nice gifts might have to wait until I'm able to. Oh no, they might be gone. All right. I'll find some nice animated gifs and show them to you on Friday. There are some tools for helping you understand why this stuff works well that are a little bit better than the pictures in the textbook. These are the ones that I'm familiar with. I don't know why they're not loading though, so I'll have to play around with it for a minute. But read the textbook, please. Read section 6.3. It will help you see exactly what's going on here, how you can think of these solids that we've used to been thinking of as disks as being cylindrical shells stacked one with inside the other, kind of like an onion. And that's the game. So after we have practiced this a little bit more, we will be done with the volume stuff. And then we're going to be moving on to talking about methods of integration. So we'll learn how to integrate some more interesting shit. But yeah, that is, I think, where I'll leave it for today. Please continue working on the homework. I don't think there's anything in there that you should find impossible as long as you take your time. I'll come back here in case anybody still wanted to write things down from this. And besides that, I will see you guys either in office hours this afternoon or in class on Friday. Take care, guys.